In this lecture, we will discuss the Fourier series representation of discrete time periodic signals. Previously, we had seen the Fourier series representation of continuous time periodic signals. Now we will build on that background and discuss the representation of discrete time periodic signals in terms of its Fourier series. So to recall, the continuous time periodic signal has a Fourier series representation given by this infinite summation as ak e power jk omega naught t. So it is being represented as a sum of scaled complex exponential signals, right, as a linear combination of complex exponential signals. So that is what the Fourier series representation is doing, where we compute the Fourier coefficients ak according to this formula, in which the value t is the fundamental period of the continuous time signal, right? Similarly, the discrete time equivalent of the Fourier series equation is the discrete signal, the discrete sequence x of n is represented as a summation or a linear combination of discrete complex exponentials, which are denoted e power jk omega naught n, where each of the kth terms is scaled by a factor ak, and this ak is called as the Fourier series coefficients of the discrete time periodic signal. So we need to compute ak, and then which are the weight functions associated with each of the complex exponential. So ak is the weight of the kth complex exponential. So we express the signal x of n as a linear combination of discrete complex exponentials in the Fourier series representation. Okay, so from continuous time we have come to the discrete time now, where x of n is discrete and also e power jk omega naught n is also discrete. And the Fourier series coefficient ak is computed by this formula, analogous to the continuous time case, where we have 1 by t. Here we have 1 by n, where n is the fundamental period of the discrete time sequence x of n, and we do the summation of x of n multiplied with e power minus jk omega naught n. So in continuous time it was integration, in discrete time it is summation over a range of n. Again, I'll come to what should be the range of k and what should be the range of n here. Both should have the same range. Whatever is the range for k, that should be the range for n as well when computing ak. But what is that range for k and hence for n? We'll come to that, because unlike in the continuous case where it is an infinite summation, here we do it over a specific range for good reasons. So we'll talk about that in the next page, but it is over some range k and on the same range of n. So whatever is the range we choose for k, it should be the same range for this n in this summation for computing ak. Now the parameter omega naught is the frequency, the fundamental frequency of the discrete sequence, which is denoted as 2 pi by n, and n is the fundamental period of the sequence x of n. Now there are a few important things that we need to remember in the case of discrete time periodic signals. Unlike in the continuous time case, where the complex exponential e power j k omega naught t or e power j omega naught t is periodic for any value of the frequency omega naught, that is not the case in discrete time. In discrete time, the frequency omega naught should satisfy a certain condition in order for the sequence to be periodic, for the complex exponential to be periodic. So what is that condition? The condition is that omega naught should satisfy this relationship of that omega naught by 2 pi should be a rational number. That means it should be a ratio of two integers. So m is an integer and capital N is also an integer, which is the fundamental period of the signal. Again, this is something that we have discussed in lecture 4, so you can refer to lecture 4 to get more details on this. So only when omega naught is satisfying this condition, the discrete complex exponential is going to be periodic. Otherwise it will not be periodic. So we've just rewritten that in a different way. We just made the inverse of this. So instead of writing omega naught by 2 pi, I've now written it as 2 pi by omega naught. So this is also inversed. So that is capital N divided by m. Okay, now we can have the small m to be equal to 1, in which case this 2 pi by omega naught is an integer n. Okay, since we have chosen m equal to 1, and hence in that case the frequency becomes 2 pi by n, which is our fundamental frequency, and the corresponding value of n is the fundamental period. So the complex exponential in that case becomes e power j omega naught n. In place of omega naught, we have 2 pi by n here. E power j 2 pi by capital N into small n, which is the index value for the samples. Okay. So this is the first important point that we need to remember. For the discrete complex exponential, the frequency omega naught should satisfy this condition in order for the discrete complex exponential to be periodic. The second important property is that if a discrete complex exponential is periodic with some period, then all other discrete complex exponentials whose frequencies are integer multiples of that omega naught are also having the same period n. So if e power j omega naught n is periodic with period n, so is e power j 2 omega naught n. 2 omega naught has a frequency which is 2 times omega naught. 3 omega naught has a frequency which is 3 times omega naught. And similarly, we can have it negative values as well. Minus j2 omega naught is having a frequency minus 2 times omega naught, and minus 3 j omega naught is having a frequency minus 3 omega naught, and so on. So all these complex exponentials whose frequencies are integer multiples of omega naught, they are also periodic with the period n. So okay, that's the second important observation that we make. So what happens is, with this information, we can create, we can write down a set of all discrete time complex exponentials that are periodic with the same period n. So it will be discrete complex exponential with frequency omega naught, 2 omega naught, 3 omega naught, and similarly minus omega naught, minus 2 omega naught, minus 3 omega naught, and we can go on and on. So we can define that entire set as phi k of n e power j k omega naught n, and this parameter k can take on all integer values. So it can be 0, in which case it becomes equal to 1. This entire term becomes 1, it's a constant. When it is plus or minus 1, we have e power j omega naught n and e power minus j omega naught n. When it's plus or minus 2, it is e power j 2 omega naught n, and for minus 2, it is e power minus j 2 omega naught n, and so on. So what we see is that each of these components is harmonically related. That means their frequencies are multiples of omega naught. So when e power j omega naught n is having a frequency omega naught given by 2 pi by n, 2 omega naught is frequency 2 times omega naught, and so on. So we call these signals to be harmonically related because each of them has a frequency that is a multiple of omega naught. Now the third property with regards to the discrete complex exponentials is that if the frequency is shifted by 2 pi, the sequence becomes identical. So if we take a discrete complex exponential with a frequency k omega naught and shifted by 2 pi, so the frequency is now k omega naught plus 2 pi, we will get back the same original sequence e power j k omega. That means discrete time complex exponentials that are different in frequency by a multiple of 2 pi are identical. So this is again something which we have seen at the end of lecture 4. If you see the last slide of lecture 4, you will see the illustration for this. So discrete complex exponentials which are having a frequency that differs by 2 pi, they become identical. So that's what is illustrated here. So e power j k omega naught n is having a frequency omega naught. Now instead of k omega naught, so we shifted that by 2 pi, and we see that we will get the same e power j k omega naught n. So because e power j 2 pi n is cosine 2 pi n plus j sine 2 pi n, which is equal to 1. So we get that when the frequency k omega naught is shifted by 2 pi, we get back the same sequence e power j k omega naught n. So the two signals become identical. Okay, so we can observe the same thing in the entire set of discrete complex exponentials that we have in general. So if we denote our phi k of n as e power j k omega naught n, then phi k plus n of n, so in place of k we put k plus n, and we see that phi k plus n becomes equal to phi k of n. What this means is that even though in our set of this phi k of n, the value of k can have infinite possible integers, which is 0, plus or minus 1, plus or minus 2, plus or minus 3, and so on till infinity, and minus infinity on the other side. However, among this entire set, there are only n distinct signals. All the others are repetitions from one of these n distinct signals. That means even though we have the set to be of infinite size, out of that entire set, there are only n complex exponentials in that set are different from each other. Okay, all the others will be replicas of one of these n components. Okay, so if the period of the signal is n, then this set of complex exponentials, all of which have the same period n, that contains only n distinct signals. Okay, that n distinct signals means only n of them are different. All the others will be repetitions of these n signals. So therefore, this influences the summation that we have in our Fourier series representation, the summation over k, right? Because unlike the continuous time Fourier series, where we have an infinite summation, in the discrete time Fourier series, the summation will be only over these distinct signals, because after that it's just a repetition. So we don't want to do the repetition, so we'll be summing it only over the n distinct values or n distinct complex exponentials. So even though we have these values for k, this is k, I should have written it as k here, for k equal to, let me correct that, that's k equal to 0, 1, plus or minus 1, plus or minus 2, and so on. So even though there is infinite set of numbers here, only n of them are distinct and different from each other. All the others are repetitions. So we have these three observations regarding the discrete time complex exponentials. First is that for them to be periodic, omega naught should satisfy a certain condition. The second is that if a complex exponential with frequency omega naught is having a period n, then the complex exponentials whose frequencies are multiples of omega naught are also periodic with the same period n. And the complex exponentials, if two complex exponentials differ in frequency by an amount equal to 2 pi or multiples of 2 pi, they become identical. Okay, so with these three pieces of information, we can say that we can decide the range of the summation in the Fourier series. Okay, so to illustrate this, that there are only n distinct complex exponentials in the set. So we have this phi k of n for k being 0, 1, 2, 3, and minus 1, minus 2, and so on. So if you go from 0 to n minus 1, that is a set of n complex exponentials, each of which has a period of capital N. So we have for k equal to 0, e power j 0, that's 1. For k equal to 1, it is e power j 1 omega naught n, e power j 2 omega naught n, so on, up to n minus 1. So 0 to n minus 1 is a set of n signals. And all of these are distinct from each other. So this is different from this. Phi 0 is different from phi 1, which is different from phi 2. So all of them are distinct from each other. Any other value of k, right, after this, after phi n minus 1, if I put phi n of n or phi n plus 1 of n, they will start repeating from this sequence. So phi n of n will be the same as phi 0, phi n plus 1 would be the same as phi 1 of n, phi n plus 2 would be the same as phi 2 of n, and so on. And similarly, if you go backwards from phi 0, if you go to phi minus 1 of n, it will be repeating from this end here. So that will be phi n minus 1 of n. And phi minus 2 of n will be the same as phi n minus 2 of n here. Okay, so basically these are the n distinct complex exponentials from this set. All the others would be repetitions from one of this set. So in general, we say that this phi k plus n of n is the same as phi k of n. So it has a period of n. And based on that relationship, we can now find which value of this becomes equal to which of these unique phi k's. Okay, so we put k equal to 0 here. So phi 0 plus n, that is phi n, becomes phi 0. Phi n plus 1. So if you put 1 for k, so it becomes 1 plus n, which is n plus 1, equal to phi 1 of n, and so on. Okay, so this is what we mean by saying, when we say that there are only n distinct complex exponentials in this set, all the others are just repetitions. So in the Fourier series representation, we only need to do the summation for the values of k which give us distinct complex exponentials. So since there are only n distinct signals, we need to make the summation over this range of n distinct signals. Okay, so in order to do that, we only need to choose the value of k to be n consecutive integers, and we can choose any range as long as they are n consecutive numbers. So this information, we denote that as k to be representing any n successive values. Okay, so to denote this as n successive values, we put these triangular brackets, the triangular parenthesis in the, around n, to indicate that k ranges over n successive values, where capital N is the period of the signal and capital N is also the number of distinct complex exponentials that we have in our set. So we can choose the n the successive integers to go from 0 to n minus 1. So that's a range of n numbers. Or we can go from 1 to n or 2 to n plus 1. We can choose any range as long as the length of that range is n. So 0 to n minus 1 has a length n, 1 to n has a length n, and so on, right? So we are free to choose any range for k which has a length of capital N, and that should be n successive values. Okay, not just any n values. The n values should be next to each other. Okay, we can go from 0 to n minus 1 or 1 to n or 2 to n plus 1, and so on and so forth. But normally we will write it in terms of 0 to n minus 1, only in specific cases where other values make the analysis or calculations easier. We will choose other ranges for k, but normally we'll follow the convention of choosing k to range between 0 and n minus 1. So our Fourier series expression for discrete time periodic signal becomes like this. The summation is our range k, which is n successive integers, and the Fourier coefficients ak is given by this equation which we have seen earlier. And this summation in the computation of ak has the summation over n, and the range of n should be the same as the range of k. Okay, so whatever is the range of k that we choose, we have to use the same range for this n as well. So that means this n should also be a sequence of n successive integers. So if we choose k to be 0 to n minus 1, then n also should be 0 to n minus 1. If we choose k to be 1 to n, then the small n should also be 1 to capital N, and so on and so forth. So this now gives us what should be the range of k and hence n in these summation terms in the Fourier series representation of discrete time periodic signals. So we normally, as I said, we will choose k to be 0 to n minus 1 most of the times, but occasionally we can choose any other range as well. That will not alter the results, but the convention we'll follow is to have a range of k going from 0 to n minus 1. So the summation will be 0 to n minus 1 for k, and that same range should be used for the small n in computing the Fourier coefficients ak. Now this equation, the first equation that we have here, where we are representing the discrete time periodic signal x of n as a linear combination of complex exponentials. We call this as the synthesis equation, and the equation where we compute the Fourier coefficients, that is called as the analysis equation. Okay, but the important difference between the continuous time and the discrete time that you notice is that in the continuous time we had this as an infinite sum, but here we have a sum which is over a finite number of complex exponentials, so it's 0 to n minus 1. And secondly, in the computation of ak in continuous time, we had this as an integral, and in discrete time, this is a summation because it's discrete. So these parameters ak, the Fourier coefficients, they are actually called as the spectral coefficients of the periodic sequence x of n. It gives us information about the frequency content or frequency domain information of the signal x of n. So let us now investigate and analyze the synthesis equation in a little more depth to get a better understanding of it. So we have this synthesis equation where each of these discrete complex exponential is from the set which we denote as phi k of n, right? So we can expand the summation as a0 phi 0 of n for k equal to 0, a1 phi 1 of n for k equal to 1, up to an minus 1 phi n minus 1 of n. So this is when we choose our range of k from 0 to n minus 1. But as we said before, we can choose this k to be any successive integers of length n. So rather than 0 to n minus 1, if we had taken k to be 1 to n, then the summation is 1 to n. In that case, this x of n, if we expand the summation, we get a1 phi 1 of n plus a2 phi 2 of n up to an phi n of n. So now we had this property that this phi k plus n of n is equal to phi k of n. Okay, we've seen this previously a couple of slides back. So that implies that this last term phi n of n, an phi n of n, is the same as the first term in this summation a0 phi 0 of n, because phi n is the same as phi 0. So this last term here, here is the same as the first term here. So basically what that means is this an phi n of n is the same as a0 phi 0 of n, because these are both representing the same sequence. This is also x of n, this is also x of n. All the other terms are the same here. We have a1 phi 1, a2 phi 2 up to an minus 1 phi n. The only term that is different is here we have a0 phi 0 of n, and here we have an phi n of n. And if these expressions are representing the same x of n, then automatically it follows that this an phi n of n is the same as a0 phi 0 of n. And since we've already shown that there are only n distinct phi k of n, after that they repeat. So this phi n of n is equal to phi 0 of n, and therefore it follows that this an is the same as a0. It implies that the an, that is the Fourier coefficients, ak's, are also periodic with period n. That means ak plus n is the same as ak. That means an is the same as a0, an plus 1 is the same as a1, an plus 2 is the same as a2, and so on and forth. So just as we have these phi k of n to be periodic with n, capital N that is, similarly the Fourier coefficients ak are also periodic with period capital N. Okay, so that's another observation that we deduce from expanding this summation. So as we said, the Fourier coefficients ak are also periodic with period n. So therefore, we need only n successive Fourier series coefficients to represent x of n. So that is why we have the summation over a range of n successive values for k, and that can be chosen to be any range 0 to n minus 1 or 1 to n or 2 to n plus 1 and so on. Okay, so what we observe is that the Fourier series of discrete time periodic signal is a finite series containing only n terms. Unlike the continuous time for the Fourier series of the continuous time periodic signal, which is an infinite series. So now that we have all the required information related to the Fourier series of discrete time periodic signals, let us now look at an example and try to understand the Fourier series of discrete periodic signals in more detail. So we'll take this example of x of n as sine omega naught n, and of course for this to be periodic, this omega naught should satisfy some condition, that this 2 pi by omega naught should be a rational number. So 2 pi by omega naught, which is given as capital N, the period, divided by m, where n and m should both be integers. So let's first take the simple case that this 2 pi by omega naught is an integer, okay, and every integer is a rational number because the denominator is 1. So we'll make this denominator small m equal to 1. So we get this 2 pi by omega naught to be an integer value, that is n. So in that case, we get that this is a sinusoidal signal, discrete sinusoidal signal, which has a frequency given by 2 pi by capital N, and the fundamental period is capital N. So we have x of n, which is sine omega naught n, and since it is now with a frequency which makes it periodic, we can now represent it in terms of the complex exponentials. This is the Euler's formula. Sine theta is e power j theta plus e power minus j theta divided by 2j, right? So we just applied this. So sine omega naught n is e power j omega naught n minus e power minus j omega naught n divided by 2j. So that 1 by 2j factor is given to each of these terms, okay? So we have this representation of sine omega naught n in terms of the complex exponentials. Now if we compare this with our Fourier series summation, this is a term for k equal to 1, e power j k omega naught n, right? E power j k omega naught n. It is a k e power j k omega naught n, where k equal to 1 here. So this first term represents the term corresponding to k equal to 1, and the second term corresponds to k equal to minus 1. So that means this is denoting, this parameter here is denoting ak, that is 1 by 2j is ak for k equal to 1, that is a1, and minus 1 by 2j is denoting ak for k equal to minus 1. So 1 by 2j is representing a1, and minus 1 by 2j is denoting a minus 1. Okay, so this is what we observe here. So this is the complex exponential for k equal to 1, and that's representing the complex exponential for k equal to minus 1. So therefore this is 1 by 2j is a1, and minus 1 by 2j is a minus 1. So from that we have these terms a1 and a minus 1. All other coefficients over the interval of summation are 0. Okay, now the summation is done over a range of n numbers, right? Within that range, all other values of ak are 0. Outside that range, because it's periodic, there will be other values which have the same value as a1 and a minus 1. Okay, and that depends on the period n, right? So if the period is some n, then something which is an plus a1 plus n would be the same as a1, and similarly a minus 1 plus n would also be the same as a minus 1, okay, because these ak's are also periodic with period n. So what we will see is that within the interval of summation, where we have only n successive values or components, except a1 and a minus 1, all the others would be 0. But outside this range, these values would repeat. A1 and a minus 1 would be repeating periodically with period n. Okay, and that is also something which we will plot soon, and it will become clearer, much clearer. So we have this. Let's fix some period for n. Okay, let's give it a value of phi. So the period n is assigned a value of phi, in which case our signal becomes sine 2 pi by n, capital N times n, which is 2 pi by phi times n. So the value of a1 is still 1 by 2j, and a minus 1 is minus 1 by 2j. And based on that, we know that these AKs are periodic. So A1 plus N would be 1 plus N is phi now. So A1 plus N, which is A6, that will be the same as A1. So that's 1 by 2J, because A1 plus N, AK plus N is equal to AK, right? So K in this case is 1 and N is 5. So A6 is the same as A1. Similarly, A minus 1 plus N, that becomes A4 is the same as A minus 1. We can have A1 plus 2N, okay, 2 times N. Since N is 5, it is 1 plus 10 becomes A11, is also the same as A1. Similarly, A minus 1 plus 2N is A9, is the same as A1. Or we can shift it to the other side. It's A1 minus N, so 1 minus 5 is A minus 4. So A minus 4 is basically AK when K is minus 4. That also is the same as this A1, which is 1 by 2J. So and so on. We can have this periodic repetition. And similarly, A minus 6 is also equal to A minus 1. So we have seen this periodicity property of the AKs. Now, we want to plot the Fourier series coefficients for this signal, discrete signal sine omega naught n, where omega naught is 2 pi by phi. So when in the range 0 to n minus 1, only a1 and a minus 1 are non-zero. So we have a1 is 1 by 2j, and a minus 1 is minus 1 by 2j. That means, and all other values are 0. That means a0 is also going to be 0. So we have here a0 is 0, a1 is 1 by 2j, and a minus 1 is minus 1 by 2j. And then these are going to repeat with period n, right? So we have a1 plus 5, which is a6 is also 1 by 2j. So we have 1 by 2j at a1, that is for k equal to 1. So the same thing we have for a6, and the same thing we have for a11. So if we go 1, 2, 3, 4, 5 steps forward, that is, since the period n is equal to 5, so this will repeat at every 5 steps, or 5 steps of k. Similarly, this minus 1 by 2j will repeat every 5 steps of k. Okay, so what is at minus 1 we'll get at 4. So a4 is the same as a minus 1, which is what we saw here. a4 is the same as a minus 1. And similarly, if we move to the left, we get these same repetitions. So when we are doing the Fourier series representation, the summation over k, the value of k should be chosen to be n successive integers, n successive values, right? So in this case, n is equal to 5. So from this plot, we can choose any 5 index values of k and add them to get our original signal sine omega naught n. So we can go from 0 to n minus 1, which is n is 5, so 0 to 4. So we can add these 5 terms from 0 to 4. Or we can go from 1 to 5. Or we can go from minus 1 to 3. Or we can go from minus 5 to minus 1. So all of them would give us the same result. So this summation interval, the range of the summation for k, can be chosen to be any n successive values. So we can choose any 5 samples from here and add them together to get our original sequence. But what we notice is that in any range of n values, there are only 2 non-zero values. One of them will be 1 by 2j and the other one will be minus 1 by 2j. All the others are zeros. Okay, so it doesn't matter which interval we choose, as long as that interval consists of n successive values for k. Okay, so that is what is illustrated here. And We can do other examples as well, where we will now have the condition that 2 pi by omega naught is n by m. Previously we chose m equal to 1, so that we had 2 pi by omega naught as an integer. Now we have 2 pi by omega naught as a rational number, because now we will choose m to be another integer which is not equal to 1, and such that m and n do not have any common factors between them. It's not like n is equal to 10 and m is equal to 2. So 10 by 2 will make it 5. If it becomes 5, then again it's an integer, but rather we'll choose n and m such that they have no common factors, so that this remains a rational number. So in that case, what we have is the fundamental period omega, the fundamental frequency omega naught becomes an integer multiple of 2 pi by n. So if this m is some integer other than 1, then the fundamental frequency omega naught is 2 pi by n times m. So it's an integer multiple of 2 pi by n. Okay, that is what we are trying to say. So our signal sine omega naught n can be written as sine m into 2 pi by n times n, because omega naught is this value. We just substitute the value of omega naught here in this expression and written it as the in the Euler's formula, writing the sine omega naught n as the sum of complex exponentials. So e power j omega naught n minus e power minus j omega naught n divided by 2j. So now this is the same, this term is denoting e power j k omega naught n, right? So this is e power j k 2 pi by n times n. So that corresponds to k equal to m. So when k equal to m, we get this term, which is what we have here. And when k equal to minus m, we get this term. So that means this 1 by 2j here in this case is representing a subscript m, and the minus 1 by 2j here is representing a subscript minus m. So we have am as 1 by 2j and a minus m is minus 1 by 2j. Previously we had m equal to 1. So we had a1 as 1 by 2j and a minus 1 as minus 1 by 2j. Now we have m to be any other integer other than 1. So we have this 1 by 2j representing am and the minus 1 by 2j representing a minus m. So let us now assign some values for the period n as well as for this parameter m. So we'll choose the period n as 5 as before, and now we'll choose the value of small m to be equal to 3. Previously we had chosen this as 1. Okay, so in that case our signal sine omega naught n, which is sine m 2 pi by n times n. So capital N is 5 and small m is 3. We substitute and we get sine 6 pi n by 5 as our sequence x of n. So in this case we have seen that am is equal to 1 by 2j and a minus m is minus 1 by 2j, which is what we have seen here. And now we know the value of m as 3. So we get a3 as 1 by 2j and a minus 3 as minus 1 by 2j. And therefore, since we have the a case to be periodic with period n, so any shift of this value of m by n will give the same value for that a k as well. So am plus n is am. So n is 5 here and m is 3. So a8 will be the same as a3, and similarly a2 will be the same as a minus 3. And like that we can compute for any other values of n, okay, which is shifted by integer multiples of n. Okay, this is minus shifted by minus n, and similarly we can have shifted by minus 2n, plus 2n, and so on. So we'll see that these AKs are repeating after a shift of 5, okay, because the period n is equal to 5. But we start with the first value, which is a3 and a minus 3 in this case. And a shift of 5 from 3 is 8 to the right, and to the left it becomes a minus 2. It's the same as a3, right? Similarly, for minus 3, it is minus 3 plus 5 is minus 2. So minus 3 plus 5 is plus 2. So a2 is equal to a minus 3. And we can work out for different values of shifts of integer multiples of n. So we'll see that these AKs are periodic with period n. Now we will plot these Fourier coefficients for this sequence x of n, which is sine m 2 pi by n times small n. So m is 3, capital N is 5. So we have, the first thing is a3 and a minus 3 are known. a3 is 1 by 2j and a minus 3 is minus 1 by 2j. So we have a3 as 1 by 2j and a minus 3 is minus 1 by 2j. Now if we shift from these points by n steps, we'll get the same value. So if a3 is 1 by 2j, 1, 2, 3, 4, 5 steps away is the same 1 by 2j. Similarly, 5 steps to the left, we'll get the same 1 by 2j. And since we have a minus 3 as minus 1 by 2j, shift this by 5, that's 1, 2, 3, 4, 5 to the right, we have the same minus 1 by 2j. Going 5 steps to the left will give us the same minus 1 by 2j. And like that we can continue, and what we see is that these values repeat periodically. And in our Fourier series synthesis equation, the summation can be chosen over any n successive values of k. So again, like before, we can go from 0 to n minus 1, that is 0 to 4, or 1 to 5, or minus 4 to 0, or minus 5 to minus 1, or we can go from 5 to 9. So we can choose any n successive values of k. We will get the same result, because what we see is that irrespective of which range we choose, there are only two non-zero values. One of them is 1 by 2j and the other is minus 1 by 2j. All the others are 0 in every range, which I have shown in these blue curly braces. Okay, so this is just to illustrate that the Fourier coefficients are periodic. And in our Fourier synthesis equation, we can choose the range of k to be n successive values of k, and that would not alter our result. Now, so far we have been obtaining the value of the Fourier coefficients ak by observation, by writing the sine function in terms of the complex exponentials and choosing the value and determining ak's by observation. But we can use the analysis equation to compute the values of ak. So you can substitute x of n in the summation, which is sine 2 pi by phi n, and work out the values of ak. So try to find a0, put k equal to 0, put k equal to 1, and so on, and compute the values of ak's and see that the answers match with what we have seen previously. Okay, so I'll leave that as an exercise for you. That is a fairly simple summation. It may be a bit lengthy, but it's not difficult. So you can do it yourself and verify that you get the value of ak to be the same as what we have obtained previously. Now, next we are going to see one more example of the Fourier series representation and finding the Fourier coefficients. And using this example, I'm going to highlight some properties of the Fourier coefficients itself. So let's take this example where we have x of n given by these sum of sinusoidal components. So we have this sine term, and this is a cosine term, and this is also a cosine term, which is also having a phase shift of pi by 2. Okay, so these are sine and cosine terms being added together to produce this sequence x of n, and each of these values of omega naught are satisfying the conditions for being periodic. So it's 2 pi by n. The omega naught is 2 pi by n. So that means omega naught by 2 pi is a rational number. Similarly, here it's omega naught is 2 pi by n, and here it is 4 pi by n. So all of them are either integers or rational numbers. So therefore, these are all periodic, and the sum of these periodic signals is also another periodic signal, which is our x of n. Now, we will represent each of these sine and cosine terms as in terms of the complex exponentials by using Euler's formula. Okay, sine theta is e power j theta minus e power minus j theta by 2j. So we have represented this sine term as this sum of complex exponentials. Okay, and the cosine term is e power j theta plus e power minus j theta by 2. So 3 by 2 has come in, so that's 3 by 2 e power j, this is theta, plus e power minus j theta. And similarly, this cosine term, the theta here is 4 pi n by capital N plus pi by 2. So it is e power j theta plus e power minus j theta divided by 2, right? So we have used the Euler's formula to represent each of these sine and cosine terms. Now we will combine the like terms. So we have this e power j 2 pi by n times small n, and we have the same term here, e power j 2 pi by capital N times small n. So we will take these common terms. So this is having a multiplying factor of 3 by 2, and this term is having a multiplying factor of 1 by 2j. So e power j 2 pi by capital N times small n is having this overall factor 3 by 2 plus 1 by 2j. Similarly, e power minus j 2 pi by n is having a multiplying factor of 1 by 2j, which is minus 1 by 2j because there's a minus here, minus 1 by 2j. And in this term, it is plus 3 by 2. So we have for this term, which is e power minus j 2 pi by n times small n, the multiplying factor is 3 by 2 minus 1 by 2j. And similarly for this, we can take the e power j pi by 2 outside because that is not having any n associated with it. The index n is not associated with this. So we can take that outside. So it is half e power j pi by 2 multiplying this e power j 4 pi n by capital N. And similarly, it is e power minus j pi by 2 multiplying this e power minus j 4 pi n by capital N. Now this 4 pi can be written as 2 into 2 pi, right? So because our omega naught is 2 pi by n, so we want to write it as 2 omega naught, right? 2 into 2 pi by n is 2 omega naught. So we have just simplified this expression and got this expansion for our x of n. So now what we see is that this term corresponds to e power j 2 pi by n times n into k for k equal to 1. This is also, this is for k equal to minus 1. This is for k equal to 2, and this is for k equal to minus 2. And this term corresponds to the term for k equal to 0, right? So we see that based on the terms and comparing the terms with the Fourier series summation expression or the synthesis equation, the first term here is a0 e power j0, which is constant. So this is corresponding to a0. This is corresponding to a1 e power j1 omega naught n. And so the a1 term is 3 by 2 plus 1 by 2j, which is what we have written here. So a1 is 3 by 2 plus 1 by 2j. Since the j is in the denominator, we multiply the numerator and denominator by j. So j by j, this is the denominator becomes j square, which is minus 1. So 1 by 2 into minus 1 is minus 1 by 2, and we have a j in the numerator, right? So that becomes 3 by 2 minus half times j. Similarly, the third term here is for k equal to minus 1. It is e power j minus 1 times 2 pi by n times n. So this is representing a minus 1. So we have a minus 1 given as this. Since again the j is in the denominator, we multiply and divide by j for this term to get 3 by 2 plus half times j. And the last term that we have here, the last two terms that we have here, this is corresponding to k equal to 2 e power j k 2 pi by n times n. So the k here is 2. So this term is representing a2. It's ak e power jk omega naught n, right? So this corresponds to a2. So half e power j pi by 2 is a2. But e power j pi by 2 is nothing but cosine pi by 2 plus j sine pi by 2. That's cosine 90 is 0, sine 90 is 1. So j times 1 is j multiplied by half. So it's half j. Similarly, the last term is having is corresponding to e power j k omega naught n for k equal to minus 2. So this is representing a minus 2. A minus 2 e power j minus 2 omega naught n, right? So we have this as our a minus 2, which is again we substitute for e power j pi by 2, that is e power minus j pi by 2 in this case, is cosine pi by 2 minus j sine pi by 2. We get minus half times j. Okay. For all other values of ak, for all the values of k, that is, ak is equal to 0, but be clear that when we say ak is 0 for all other values of k, it means all other values of k in the interval of summation. Okay, so the interval of summation, okay, when we do the interval of summation here, it is for n successive integers. After that, it is going to repeat. So within that n successive integers, except the values which are non-zero, all the others are 0. That is what we mean to say here. Okay, so ak is 0 for all other values of k in the interval of summation of the Fourier synthesis equation. So what we notice here is that for this particular case, we have a1, which is 3 by 2 minus half times j. A minus 1 is the complex conjugate of a1, right? So a minus 1 is the complex conjugate of a1. That means the imaginary part, the sign is changed. Similarly, a minus 2 is the complex conjugate of a plus 2, right? So a minus 2 is having the imaginary part whose sign is opposite from the imaginary part of a2. So what we notice in this particular example is that each of the ak's is such that the a minus k and ak are complex conjugates of each other. So a minus k is the complex conjugate of ak, which is ak star. And similarly, ak is the complex conjugate of a minus k. And this is true. This is again something which we have discussed in the properties of Fourier series for continuous time as well. For signals that are real, the Fourier coefficients for negative indices of k are the complex conjugates of the positive indices of k. So a minus k is the complex conjugate of ak, and that is true for real signals. That means the signal does not have an imaginary part. So our signal that we have used in this example is a real signal because it is using sine and cosine. So each of these components is a real signal having some frequency, and therefore x of n is a real signal, and therefore all the ak's satisfy this property that a minus k is the complex conjugate of a k, and vice versa. Okay, furthermore, the ak's are going to be periodic as well. Okay, so an will be a0, that is ak plus n is a0, a1 plus n is a1, a1 plus 2n is also a1. So any shift by an integer multiple of n will give us the same value for ak as well. So that is something which we are familiar with. Okay, so just as the phi n's, the phi k's are periodic with period n, the ak's, the Fourier coefficients, are also periodic with period n, and that is also observed for this particular case. Now what we are going to do is, since we have these Fourier coefficients which are complex numbers, okay, we will plot different aspects of this. We'll plot the only the real part of these Fourier coefficients. We'll plot only the imaginary part and see what it is like. Then we'll plot the magnitude of each of these Fourier coefficients, and then we'll also plot the phase of these coefficients and observe how they behave. So let us see the plots of each of them. So first we will plot the real part of the ak's. So we have the ak's depicted here, represented here in this box. So the real part of ak's, so for a0, it's a real number, so the real part is that real number itself. So a0 is 1, so we have k on the x-axis and the real part of ak depicted on the y-axis. So a0 has a real part equal to 1. A1, the real part is 3 by 2 because it's a real part minus j times the imaginary part, right? What is with j is the imaginary part. So 3 by 2 is the real part, minus 1 by 2 is the imaginary part for A1. So for k equal to 1, the real part is 3 by 2, which is 1.5. For a minus 1, that is for k equal to minus 1, the real part is again 1.5, which is 3 by 2. Now, So we have a1 and a minus 1. Next we have the real part of a2. If you notice here, a2 is just having the imaginary part. So the real part of a2 is 0. So for k equal to 2, the real part is 0, and for k equal to minus 2 also the real part is 0. And this sequence will repeat itself after with a shift of n, because k plus n is the same as ak. So after a shift of n, the same thing will repeat. So what we have at a0, we'll have it at an, and we'll have it at a2n, and so on. What we have at a1, we'll have it at an plus 1, and what we have at a2, we will have it at an plus 2. What we have at a minus 1, we'll have it at an minus 1. So this sequence from minus 2 to plus 2 will repeat itself. Now I put this extra dot to say that we don't know what is the value of n, so after some interval the n will repeat. Okay, so this is our main sequence, and that is repeating itself here. So this is just a gap. Okay, depending on the value of n, this may be having 10 steps forward or 15 steps forward, depending on the value of n. Okay, I've just shown one gap here. After that, the same thing repeats. So there's a single gap here, and then the same thing repeats. Similarly on the left side as well. So the coefficients will repeat themselves. So what we have plotted here is the real part of the Fourier coefficients for each of these AKs. So similarly, we can plot the imaginary part of these Fourier coefficients. So in this case, the imaginary part for the first term for a0 is 0. It's 1 plus j0. So the imaginary part is 0 because a0 is real. So the imaginary part is 0 here. And corresponding to a1, the imaginary part is minus half. For k equal to 1, it's minus half. And for k equal to minus 1, it is plus half. For k equal to 2, it is plus half. And for k equal to minus 2, it is minus half. So that is one entire sequence on one set of these Fourier coefficients, and these will repeat after with an n after n samples, right? So we will see that they repeat after n. So the 0, the a0 term, which is 0, it repeats at n, at 2n, and so on. Similarly, and it repeats at minus n, minus 2n, and so on. So in between, I have just placed some samples as gaps, okay, which are all going to be 0, and I've shown here 3. Depending on the value of n, we will have that many. We will have the appropriate number of samples here in between. Okay, I've just depicted 3 just for the lack of space. Okay, so but this entire sequence is repeating, centered on n, centered on 2n, similarly centered on minus n, centered on minus 2n, and so on. So this is the plot of the imaginary part of the Fourier coefficients. Next, we will plot the magnitudes of the AKs. So these are all complex numbers. So we'll take the magnitudes. For the real case, for A0, the magnitude is itself. So that's 1. For these complex numbers, the magnitude is square root of the square of the real part plus the square of the imaginary part. So because A1 and A minus 1 are complex conjugates of each other, their magnitudes will be the same, which is equal to the square of the real part plus the square of the imaginary part under the root. So that gives us root 10 by 2. And for A2, again, the magnitude of A2 and A minus 2 are same because they are complex conjugates of each other. And here the real part is 0. So it is 0 square plus half square under the root. So we get simply half. So now we can plot the magnitudes of these Fourier coefficients, AKs. So we have k on the x-axis and the magnitude of ak on the y-axis. So for k equal to 0, we have a magnitude of 1. So that's a height of 1. For k equal to 1 and minus 1, the magnitude is root 10 by 2. which is root 10 is just over 3, right? So just over 3 by 2, just over 1.5. So it's here, that's root 10 by 2 for 1 and minus 1. And for a2 and a minus 2, the magnitude is half. So we have it at a height of half. So that's one set of these signal, of these Fourier coefficients, which we will mark like this. And this entire thing will repeat at integer multiples of n. So what we have at 0, that occurs at n. What we have at 1, that occurs at n plus 1. What we have at 2 occurs at n plus 2. What we had at minus 1, it occurs at n minus 1. And whatever is at minus 2, that repeats itself at n minus 2. So that's the second repetition occurring at n. And similarly, we'll have this third repetition at 2n. And similarly, that's at minus n. And we'll have at minus 2n and so on. And again, I have shown here only 3 blank spaces here. We don't know the value of n, we haven't fixed it. So this entire pattern is going to repeat at integer values of n. So at n, at 2n, and 3n, and so on. So that's the magnitude spectrum. We call this as the magnitude spectrum of our sequence x of n, where we have plotted the magnitudes of the Fourier series coefficients of the sequence x of n. Okay. Similarly, we can plot the phase spectrum. So where we compute the phase of each of these Fourier coefficients and plot them as a function of k. So again, for a0, the phase is 0. So we have 0. For a1, the phase is the formula for phase is tan inverse of the imaginary part divided by the real part, right? So the imaginary part is minus half, and the real part is 3 by 2. So that gives us an angle of minus 0.3215. And because a minus 1 is the complex conjugate of a1, their phases will be having opposite signs. So if this is minus, this is plus. Similarly, for a2, the phase is 90 degrees, which is pi by 2. And for a minus 2, because it's a complex conjugate of a2, the phase will have the opposite sign. So it's if this is plus pi by 2, this is minus pi by 2. So we have just plotted that. So for a0, the phase is 0. For a1, it is minus 0.3215. For a minus 1, it is plus 0.3215. For a2, it is plus pi by 2. And for a minus 2, it is minus pi by 2. So that is one set of phases for one range of k. And it repeats at integer multiples of n. So what we have at 0 is at n, what we have at 1 is at n plus 1, and so on. So we have this repetition at integer multiples of n. Okay, and again, I've just shown here 3 blank spaces here between one period and the other repetition. Okay, depending on the value of n, we'll have an appropriate number of these blank 0 values. Okay, so that's the phase spectrum of the sequence x of n, where the phases of the Fourier coefficients are plotted as a function of k. Okay, now having seen all these plots, we can make a few observations. The first observation is that the real part of AK has even symmetry. If you look at the plot for the real part, what we have at plus 1, we have at minus 1, right? So the plot is even symmetry. If what is on the right hand side of this plot is a mirror image of the left hand side, and vice versa. So the real part of AK is having even symmetry. The imaginary part of AK is having odd symmetry. Whatever is at 1, we have the same value but with opposite sign for minus 1, right? So if this is minus half, this is plus half. If this is plus half, this is minus half, right? So the imaginary part of the Fourier coefficients exhibit odd symmetry. Okay, that is the second observation that we have made here. And next, if you look at the magnitude spectrum, it also has even symmetry. So the magnitude spectrum, you see, the right side of the plot is a mirror image of the left side and vice versa. So what we have at A1, we have it at A minus 1. What is at A2 is also available at A minus 2. And the same thing, okay, the about the vertical axis, it's a mirror image. So it has even symmetry. So the magnitude spectrum is having even symmetry. So that's our observation here. And the phase spectrum is having odd symmetry. So if you look at the phase spectrum, okay, it's odd symmetry. At 1 we have minus 0.32, at minus 1 we have plus 0.32, at 2 we have plus pi by 2, at minus 2 we have minus pi by 2. So this is exhibiting odd symmetry. So the phase spectrum has odd symmetry. Okay, these are important observations that will be useful in your other courses as well in higher levels. Okay, so these are some important observations. The other observation is that if you recall, when you have the signal to be periodic in the time domain, it is discrete in the frequency domain. That means even for the continuous time periodic signal, the Fourier series representation is discrete. So periodicity in the time domain corresponds to being discrete in the frequency domain. Okay. Now, in this particular case, we are dealing with the Fourier series of discrete periodic signals. So the signal is discrete in the time domain, and we see periodicity in the frequency domain. That means all the Fourier coefficients that we see here, they are all periodic. You see, it's repeating at n, 2n, at minus n, minus 2n, minus 3n, and plus 3n, and so on. So this structure is periodic now, right? So because we are dealing with discrete time signals, the Fourier coefficients are periodic. Same is observed for the imaginary part. So what we have here, it's repeating at integer multiples of n. Similarly for the magnitude, what we have centered on 0, we have a repetition at n and 2n and minus n and so on. So what we observe is that when there is discreteness in the time domain, in the frequency domain, we are going to see periodicity. Okay, again, that's an important observation that you will study later when you're studying digital communication. And in this particular case, in today's lecture, we have discussed about signals which are discrete as well as periodic. So the signals are discrete periodic signals. And we took the Fourier series of discrete periodic signals. So in the time domain, the signal is discrete and periodic. And therefore, in the frequency domain, it is also discrete and periodic, because periodic in the time domain means discrete in the frequency domain, and discrete in the time domain means periodic in the frequency domain. So let me mark that. So discrete in the time domain corresponds to periodic in the frequency domain, and periodic in the time domain corresponds to being discrete in the frequency domain. Okay, these are some important observations related to the plots of the Fourier coefficients that we have seen. Okay, we'll stop here for today, and we'll continue with the next topic in the next lecture.